I hope everybody is fine. And in this video, I'll be talking about the application of variational principle that we have already discussed in the previous video. And I'll subject this variational principle to calculate the ground state energy of hydrogen atom. And if I repeat the variational principle in quantum mechanics, it basically provides a way to have approximate a ground state energy of a system by choosing a trial wave function. And then what we do is we minimize the expectation value of the Hamiltonian, and then this principle accordingly ensures that this expectation value is always greater or equal to that of true ground state energy in case of excited to ground state energy. Now here in this video we have to I would like to estimate this. So the goal of this video is to estimate the ground state energy of one-dimensional hydrogen atom. So we're treating it as one-dimensional, and using this variational principle. And to start with, we can have a one-dimensional Hamiltonian for hydrogen atom. And what we do here is we ignore basically the spin of the electron, and we also ignore the relativistic effects. So what will be the Hamiltonian? The Hamiltonian is simply kinetic energy operator plus potential energy operator. Okay, so this is my Hamiltonian, and I can write down this H as minus H cross square by 2m d2 by dx2, this minus. So the potential energy between the nucleus and the electron is minus E square by 4 pi epsilon naught x. So this is my first term, and this first term is basically the kinetic energy operator, and the second term is the potential energy operator for the Coulomb attraction that exists between the nucleus and the electron. And x is because it's a one-dimensional case, so we have taken just one component. Now the important thing here is that what we have to do is we have to choose a wave function. We have to choose a trial wave function. Trial wave function. And let us choose this trial wave function that reflects the expected behavior of the system. Now, I think the common choice here will be to choose this trial wave function psi of x as a e to the power of minus alpha x square, where this a is the normalization constant. I should write this is normalization constant. And what does that mean? Okay, a is a constant, and it has to be calculated using the normalization. And alpha that is here, this alpha is a variational parameter. It's a variational parameter. It's a variational parameter. All right. This is the parameter that we are supposed to adjust to minimize the energy of the system. Now, what do we mean by normalization is that means the integral from minus infinity to infinity and psi of x whole square dx equals 1. This is our condition. This is what normalization means. And we can substitute the value of this wave function into this normalization condition as minus infinity to infinity. A e to the power of minus alpha x square whole square dx is equal to 1. Now, proceeding from here, what we will have is this a will come as a square, and what will be left, so we will have a square integral minus infinity to infinity, and then e to the power of minus 2 alpha x square dx will be equal to 1. Okay, so this 2 will come here, so this is e to the power of minus 2 alpha x square dx equals 1. A is a constant, this a is out, and we have a standard integral here. This is a standard Gaussian integral, that is minus infinity to infinity e to the power of minus 2 alpha x square dx. This is standard Gaussian integral, and we will directly substitute its value, and what's its value? Its value is under root of pi by 2a. So we can use it here in our equation of normalization. So this is a square times under root of pi by 2a equals 1. The eagles are banging outside. Okay, so from here I can calculate this a. So what will be a? So a will be 2 alpha up, divide by pi whole to the power of, it has whole to the power of 1 by 2, so it will become whole to the power of 1 by 4. Now this is my a, and I can write down my trial wave function. What's that? Psi of x is a e to the power of minus alpha x square. A we have calculated, and we can write down this wave function. So what will be that? That will be psi of x is, instead of a, I will write 2 alpha by pi whole to the power of 1 by 4 e to the power of minus alpha x squared. So this is my wave function. Okay, now what is important is that I have to calculate the expectation value, and in order to calculate the expectation value of the Hamiltonian, and my Hamiltonian is made of kinetic energy operator, and it's made of potential energy operator, so I have to calculate the expectation value of kinetic energy operator. Now, in order to do that, so what I have to calculate? I have to calculate the expectation value of kinetic energy operator. And in doing so, I think the right choice is to calculate the double derivative of this wave function. So if I take its first derivative, so this is d psi by dx with respect to x, what I'll get, I think here I will have the internal derivative of this exponential function, that will be 2 alpha. So this 2 alpha by pi whole raised power 1 by 4 times this is whole constant here, and here the derivative will give me minus 2 alpha times e to the power of minus alpha x square. So this is my first derivative, and what will be the second derivative? So here I'm missing something, because it's alpha. This is d by dx of alpha x square. So differentiation of x square is 2x. So this is alpha 2x. So this is alpha x and 2 alpha and x. That should be the case. So now so this whole thing is a constant, okay? And we can keep it out. And now if I have to take another derivative, so I will differentiate this again with respect to x. So I'll get d2 psi of x by dx2. I will not write this thing, okay, for the time being. I'll keep it as say something like zeta. So this is zeta times Now I'll have UV rule here to be utilized. So what I'll have say x as its into differentiation of this. The differentiation of this will give me the same thing, that's minus 2 alpha x e to the power of minus alpha x square, and then v as its, that means e to the power of minus alpha x square, and the differentiation of x will give me 1. Now let me move on to the next page so that I can write down this. So I will have d2 psi by dx2 will be, so I will use this zeta as well now. So that is 2 alpha by pi, 2 alpha by pi whole raised power 1 by 4. Then I have minus 2 alpha out. Then inside what I'll have, I will have this minus 2 alpha x square. Okay, so this is minus 2 alpha x square e to the power of minus alpha x square, then plus e to the power of minus alpha x square. Okay, this should be the case, and we can see here what we will get is we will get 2 alpha by pi whole raised power 1 by 4, and what you will have, this will be minus minus plus, 2 2s are 4, this is 4 alpha x square, then minus, okay, so this minus will make it minus, so minus plus is minus, then 2 alpha, and what will be out is e to the power of minus alpha x square. So this is my double derivative of this wave function dx2. And now what we can do is, if we have to calculate its expectation value, now let me call the expectation value of kinetic energy as T. So T refers to the kinetic energy. What will be that? That will be minus h cross square by 2m, then integral minus infinity to infinity, then we'll have psi of x, then d2 by dx2, and then psi of x, so it should be complex conjugate of it, then you'll have dx. And we can use d2 by dx2 in this integral, and after evaluation its value will come, this whole thing will give us alpha, so we'll get minus h cross square alpha by 2m. So this is my expectation value of kinetic energy. So I may call it 1 for the time being. Okay, then what we are supposed to do is we are supposed to calculate the expectation value of the potential energy. And what we have is we have the potential energy operator. So now expectation value of potential energy term. And what is that? That is, we can write down the expectation value of potential energy as minus e square out, 4 pi epsilon naught out, then integral minus infinity to infinity. Then we will have psi of x by x, the magnitude of x, whole, not whole, the square of this wave function, and divide by magnitude of x, which is linked with the potential energy operator. Okay, so here we will have dx, and on evaluating this integral we will get the expectation value of potential, and using the same approach and using the value of the integral directly, we will have minus e square by 4 pi epsilon naught, then under root of 2 alpha by pi. So this is our expectation value of potential energy. So we have calculated the expectation value of kinetic energy. What is that? That is minus h cross square alpha by 2m. Then we have calculated it for the potential energy, that's minus e square by 4 pi epsilon naught under root of 2 alpha under root of 2 alpha by pi. Now what is, so I should write down this, I should write down this E. The total energy is then the expectation of the kinetic energy plus the expectation of the potential energy. All right. So I can write this E equal to. So this E will be equal to, what was that? That was minus H cross square alpha by 2m, then minus E square by 4 pi epsilon naught, then under root of alpha, under root of 2 alpha by pi. Now, what we have to do here is we have to use the condition of minimization. That's the part of the variational principle. Now, to find the optimal value of this alpha that we have the variational parameter incorporated in the trial wave function. Then for that, to calculate this value, for that we have to minimize the energy. So if we have to minimize the energy with respect to alpha, so for calculating alpha, we minimize energy with respect to this variational parameter alpha. So for that, the derivative of this E of alpha with respect to alpha must be equal to 0. And to take the derivative of this equation with respect to alpha is the easiest thing a person can do. And by doing so, after minimizing, what we find out is that this E approximately, call it approximately, its value comes out to be nearly, will be the right thing, minus 13.6 electron volts. Minus 13.6 electron volts. So this value is very close to the known exact value for the hydrogen atom in the ground state. So we can see the beauty of using this variational principle. I think I have misquoted the sign here, because on evaluating this integral, we come up with some negative and this becomes positive. One of them has to be positive, only then we will have negative. So this is positive, and finally what we obtain is we obtain the ground state energy, the approximate ground state energy of what we call this as hydrogen atom. Now in the next video, I think I'll be discussing the same thing for a simple harmonic oscillator. I mean, we'll use variational principle to calculate the approximate energy of the simple harmonic oscillator.